Good morning, everybody, and I'd like to welcome you all to the third webinar organized by NC Energy Hub for the Energy Pathfinder project. I'm Jose Ospina, project manager for the Energy Pathfinder project. I work for Cork Centre of Architectural Education at UCC. We have 5 partners in the project. There's UCC Cork Centre. There's NC Energy Hub, who is organizing and hosting this webinar. There is the Oulu University of Applied Sciences in Finland, the Umea, the University of Umeå in Sweden, who is kindly presenting at this webinar. And there is the Landsverk organization, heritage organization from the Faroe Islands, and Historic Environment Scotland. Now, I hope you can all hear me. Let me just check that my microphone is not muted. Cleona, could you just confirm to me that everybody can hear me okay? Right.
All good, Jose. Yeah, everybody can hear you.
Thank you. Sorry for that. Okay. Now we have 14 people currently attending, so we have muted all your microphones, and apologies for that. What we'd ask you to do is to use the chat facility, which is at the bottom of your screen, and please have a look there. At the bottom menu, there's a chat facility. Now, if you have any questions, and I can see that some of you replied to my answer about sound, and you've said the sound is low. I'll do something about that now if I can. But basically, if you could please enter any questions that you might have onto the chat facility, and after our speaker finishes, we will actually go through the questions. Now, just to give some background, Energy Pathfinder is a European project funded under the Northern Periphery and Arctic Interreg program. We include those 5 partners that I've mentioned from 5 different regions in the Northern Periphery. It's actually 6 partners, sorry, from 5 different regions, because there are 2 Irish partners, UCC and NC Energy Hub. The aim of the project is to look at roadmaps and tools for achieving near zero energy in historic buildings. And partners have selected a number of historic buildings in their region that they will be either retrofitting to a very high energy standard or looking at proposals for retrofitting to a high energy standard. We'll also be doing some energy monitoring to look at the impact of those improvements from the original condition of buildings. If you'd like to find out more about the different demonstrators that we're looking at, could I suggest that you look at our website, www.energypathfinder.eu, where you'll find details of each one of them. Each one is different. And on the basis of the experiences of proposals for retrofitting these various demonstrator buildings, we intend to produce a roadmap and a tool, an online tool, to allow the owners of historic buildings to actually move towards near zero energy, based on the experience of the 6 demonstrators that we are looking at, and also other experiences from the projects. that we might gather. So without further introduction, I'd like to hand over to our main speaker, Dr. Ying Zhang from the University of Umeå, who is a lecturer and a postgraduate researcher, postdoctoral researcher at Umea, and has been carrying out research into their historic demonstrator. So, Ying, could I hand over the screen to you?
Okay, thank you. Thank you for the introduction. Maybe I can share the screen without.
Yes, sorry, I have I've got to allow you to share the screen, so just give me a minute. Now, for some reason, just a minute.
Okay, no hurry.
I thought that was done, but it obviously isn't. Okay. There you are. You should be able to share your screen now.
Okay, can you see the screen?
Yes, we were looking at your slide a minute ago, but the screen has now changed, and we're looking at something else.
Oh.
So could you change back to your presentation? You were there a minute ago.
Okay. How about now?
Yes, that's it.
Okay. Okay, good morning, everyone. I'm very glad to have the opportunity to give a presentation here. The project is based on the project of Energy Pathfinder, and I'm working in Umeå University now, and I got my PhD from Xi'an University of Architecture and Technology. And now between these two universities, we have some collaborations based on the large single zone building and the ventilation, things like this. So I'll just begin. The full title of the presentation is Energy Use and Thermal Comfort in a Large Single Zone Building During Cold Season in Umeå, Sweden. There are mainly 4 parts of the presentation: background, method, result, and the conclusions. First, I'll introduce the background. So what is a large single zone building? Mainly about the characters. It has a large height, just like some concert hall or auditorium. The total height of these buildings are 10 to 20 meters. And this kind of building also has a large ratio of external wall area to floor area. For example, for the normal office buildings, the ratio is 0.2 to 0.3 square meter per floor square meter. But for the large single zone building, the ratio will be maybe 1 square meter per floor square meter. And for these kinds of buildings, it has always has a large occupation density, like this. So based on these characters, what are the challenges to the thermal environment of the large single zone building? These 2 factors do result in a large energy use when we try to build a acceptable thermal comfort and a good air quality. For when people think about the thermal comfort, it's mainly a feeling in mind. Many people, different people have different feelings about the thermal comfort, but with the research of the thermal comfort, we find it can be evaluated by specific indices such as predicted mean vote and predicted percent dissatisfied. For example, PMV is an index that predicts the mean value of thermal sensation votes. It has some categories from -3 to +3, represent cold, cool, slightly cool, and so on. And for PPD, it is an index which can be determined from PMV. It represents the percentage of thermally dissatisfied people. So with these indices, we can evaluate a building, and for most people, the result can represent the feeling of most people. To study the thermal comfort and the energy use in large single zone building, we take the Teg church as an example to carry out the study. The church is located in Umeå, Sweden, which was built in 1969. It's just before the common sense of energy crisis. So at that time, the electric floor heating and the floor air supply and the return ventilation were used in the church. And the large windows we can see from the picture, large windows were adopted for good architectural design and the need of more daylight. As a result, a large amount of energy is used for heating per year, around 110 to 120 megawatt hour. However, the cold droughts are still complained by the visitors. So we build up the physical model here. The built space in the church is a combination of multiple interconnected cubes. The total floor area is 32 meters times 24 meters, and the highest ceiling in the building is above the altar with 20 meters, and the main hall, the height of the main hall is 16 meters. We do the field measurements to check out the HVAC facilities and the envelope condition. The floor heating works well during the cold season, and there are some small leakages around the main door. When the ventilation system was used before 2010, but now it is turned off due to the reason of energy saving. And the vertical air temperature difference in the church is small. The temperature difference is 0.3 to 1.7 Celsius degree, and there is no strong thermal stratification inside. When there is no big events, the daily visitors are around 10 to 20% per day. But when there is a big event, like the Christmas event or the St. Lucia event, there are 200 to 300 visitors. To investigate the energy use and the thermal comfort, field measurements and simulations were carried out. As I just mentioned, before 2010, the ventilation was used, but now it is turned off. So we do the measurements, and we also analyzed the old data from the church staff. They have some document about the air temperature and the relative humidity parameters like this when the ventilation was working. So based on this, we simulated the energy use by EDA-ICE, which is a software developed in Sweden. And we also predict the indoor airflow by computational fluid dynamics. So there are two parts for the simulation. One is for energy use. Which is carried out by EDA-ICE. The other one is the CFD one. For the EDA-ICE simulation, the numeric model is based on detailed construction dimensions in Table 1 and HVAC facility control strategies in Table 2 and the schedule of occupants and lights in Table 3 and Table 4. Based on these informations, we also have the meteorological data from ASHRAE 2030, which was imported into the model. And we also have a small climate station in the department building of Umeå University. So we compared the data from ASHRAE and the data from our own climate station. Based on those boundary conditions, we have the results of electricity use for the floor heating. For annual electricity using, the predicted results is 112.6 megawatt hour, while the measured results is 121 in total. The deviation is 6.9%. In most of the months, we can see from the figure, the predicted electricity using is lower than the measured one, also called the, we recorded from the electric meters. There are maybe two reasons for this. One is the air temperature in the church is controlled manually, not a sensor. So the church staff control the air velocity around 20 Celsius degree, but it is not as precise as when sensor do it. So this is the first reason. And the second reason is we can just see from the climate data, there are some difference between the ASHRAE data and the data we collected in the climate station, especially for the solar radiation. The ASHRAE data is much larger than the climate data we have in the department. And we also compared the indoor air temperature. I analyzed the data for respectively for two parts. One is for the heating reason and one is for the non-heating reason. During the heating reason, the average measured indoor air temperature is 19.7 Celsius degree, while that of the simulation is 20 Celsius degree. And during the non-heating season, the indoor air temperature varies a lot with the outside temperature. The ratio of the predicted results to measured results range from 0.83 to 1.35. We can see for most of the time, the temperature is overestimated here. The reason for this is similar to what I just mentioned above about the climate data we use in the software. And another part for simulation is the CFD. The airflow in the building is described by the basic governing equations here. And we choose LES, the large eddy simulated model, to predict the instantaneous flow characteristics and solve the turbulent flow structures. To simulate the airflow outdoors to simulate the effect of airflow outdoors on the indoor environment via the wind pressure on leakages, we use a calculation zone to simulate that. The calculation zone is covered the physical model, and the blocking rate here, this area, the ratio of this area to this area is called a blocking rate. The blocking rate in this study is 4.7%, as we mainly focused on the air pushed into the church instead of the detailed airflow around the building. And we use a steady condition for the CFD simulation. Here I listed the steady condition of the surface temperature and the outdoor air velocity and so on. Based on these conditions, the results of field measurements and the predicted ones are compared here. For air temperature, the differences between the measured ones and the predicted ones are within 0.5 Celsius degree. And for the surface temperature, the differences are within 0.3 Celsius degree. Then we, after the simulation, we have the results here. There are two modes for the church. This mode is for the year before 2010, and this mode is used now. The old mode is a floor heating plus 17 Celsius air supply, and the mode we use now is floor heating and some small exhaust fans. From the energy balance, we can see the common ground for both modes. The largest heat loss comes from the envelope, around 73% to 77%, followed by the window heat loss. It's about 12%. And another common ground for both modes is the heat loads. The heat loads are mainly undertaken by the floor heating. The rest parts of the heat loads are covered by the lights and the occupants. For each month, the heat from the lights is almost constant, but they are very small. And the differences for the two modes are the heat loss of infiltration and openings. In this mode, the heat loss of infiltrations increased 7.6%. Because when the exhaust fans are used, the air is extracted from indoor environment, and due to the balance of the air rate, the outdoor air will be sucked in to the indoor environment directly. So the infiltration heat loss increased. And compare the energy use for both modes, we can see the mode of floor heating plus air supply costs 7.7 megawatt hour than the mode of floor heating plus exhaust fans. For different categories here, just for energy use of floor heating, this mode is less than this mode due to the exhaust fans suck air from indoor. And for the second categories, the floor heating is larger. The energy use is larger for floor heating because there is no air supply in this mode. And for the energy use of air transfer system, mainly used by the fans, when there is air supply in the church, the ducts and the fans are needed. So a larger energy use for air transfer system. From this slide, we can see this mode has less energy use, but it also has its problem, because due to according to ASHRAE standards for multiple use assembly, when there is when the air rate need by people calculate by people, the outdoor air rate is 3.8 liter per second person, while when calculated the rate by area, the outdoor air rate is 0.3 liter per second square meter. So for the floor heating plus air supply, the airflow rate is 1,800 cubic meter per hour. But when the exhaust fans are used, they're only 290 cubic meter per hour airflow rate. So this mode can allow the church have big events, but this mode can only allow the church have some daily events. So we try different strategies to see if there is any possibility to save more energy. There are 4 more strategies we try to carry out. The main idea for these 5 cases are we use a night set point of temperature in the church. For case from 3 to 6, the daytime hour is from 7 a.m. to 4 p.m. And for this one is from 7 a.m. to 10 p.m. And the different night set point of air temperature is here. The more strategies we try to carry out is the mode with only air exhaust. And from Monday to Wednesday and Friday to Sunday, the duration is from 7 a.m. to 7 is from 7 p.m. And when it comes to Thursday, there are some evening events, so the hour is a bit of late. With those strategies, we have the electricity used for heating under different operation modes. For a constant set point temperature all day compared to mode 1, here we can see from the figure, electricity used for mode 2, the green one, is 4.8% less. And when the strategies are used only with exhaust, here, these strategies, except mode 1, mode 2 to mode 7 are all the strategies with only exhaust. So we compare these results to the mode 2 with different night temperature adopted, the energy saving can be 10.8% to 16.3%. And for the mode 6 and mode 7, for the same night temperature as 15 Celsius degree, but different night hours, the energy use of long night temperature hours are 8.1% more. Though the night hour temperature can save energy, but it also brings problems. When night temperature is used, it results in indoor air temperature less than the set point in the next day during work hours. For example, when a night temperature of 17 Celsius degree is used, the air temperature indoor can get back to 20 Celsius degree when it's 11 o'clock in the next morning. So there will be some hours later than people have entered the church. Time taken from the air temperature reach 20 Celsius degree ranges from 1.8 to 4 hours on the coldest day. During the coldest months, the average air temperature difference of night set point can be 19.5 to 20 Celsius degree. During most of the time, the air temperature is larger than 18 Celsius degree, but there are still some outliers out of the range of 18 Celsius degree. So we try to investigate the possibility of ventilation with warm air as a supplementary during air temperature lagging. These are cases we use in the airflow prediction. And I list all the results in the figure. This one is for the indoor air temperature with different ventilation strategies. The set point temperature at night is used as the boundary condition of wall temperature. The wall temperature has the most effect on average air temperature indoor of different locations. When the wall temperature increase 1 Celsius degree, the mean air temperatures increases about 0.7 Celsius degree. The air velocity has the least effect on the average air temperature. When the air supply velocity changes, the air temperature almost don't change. And this one is for the air velocity indoor with different ventilation strategies. Different ventilation strategies have little effect on the indoor air velocity. The air velocity varies from 0.14 meter per second to 0.18 meter per second. So it's just below the 0.2 meters per second. It has some very small variations under different ventilation strategies. With the parameter of air temperature and air velocity, we calculate the PPD. As I mentioned in the background, the predicted percentage dissatisfied people. Similar to the indoor air temperature, the wall temperature has the most effect on PPD of different locations. When the wall temperature increase 1 Celsius degree, the PPD can decrease about 6%. And when I calculate the PPD, the relative humidity and the clothing insulation are assumed because in the cold region, the water vapor in air doesn't have much effect on the heat transfer. So I just use the relative humidity from the measured data and have a range for them. When the mean relative humidity increase 10%, the PPD will decreases around 2%. We can see from here. The black one is the 20% relative humidity, and the red one is the 30% relative humidity. When the relative humidity increase, the PPD decreased in some level. And there is another factor about the clothing. When we increase the clothing of 0.2 clo, the PPD will have a larger decreasing, around 8% to 9%. The clo unit here is a unit represent the insulation of clothes we wear. So it mainly represents the thermal insulation. And we also analyzed the PPD for different locations in the church. As inlets are not evenly distributed in the church, PPD varies with the distance from the entrance. For the same air supply velocity, the farther from the range of warm air inlets, the larger the PPD is. And for the same location, when the distance between the two inlets increases, the PPD also increases. So above all, we have some conclusions in the large single zone building. Numerical models for energy use are predicted, and airflow simulation have been validated for the large single zone building. And for the prediction of energy use, when constant set point temperature is used, the strategy with lower air supply temperature is used, the energy use is 4.8% larger than the strategy with only exhaust vents. For different 9 set point temperature, the energy uses decreased 10.8% to 16.3% compared to the mode only with exhaust. And when 9 set point temperature strategies are used, there are 1.8 to 4 hours before the air temperature get back again to the target temperature as 20 Celsius degree we hope it is, which visitors can have a good thermal comfort. And ventilation with warm air supply can work as a supplementary for heating before the air temperature reach the target under the condition of steady state. And for the ventilation strategies, the wall surface temperature has the most effect on the thermal comfort indices. So that's all. That's my presentation. Thank you for all your attentions. Thank you. So
You here? Yes, hello.
Yeah.
Thank you, Singh, for a very interesting and very comprehensive presentation. Now, we have a few minutes left for questions. I haven't seen that many questions on the chat. What we're going to do is I'll take a couple of questions that are there at the moment, and then immediately we'll unmute the microphones to see if anybody wants to add anything else. I think that it's extremely interesting, the scientific method of modeling a numerical estimation of the effect of airflow on a building like this that you've shown, and it really is very cutting edge. Could you explain? You mentioned two options for the heating. One was, I think, airflow, and the other was exhaust. I don't know if I certainly am not entirely clear as to what those options actually are. Could you just elaborate? Is it different forms of heating that you're talking about there?
Yeah. Here.
So presumably one is what, like heat pumps, and another one is like something else?
Yeah. For the Tegs church, the mainly heat load is undertaken by floor heating, use electricity. Yes. Yeah, some wire, thermal wire. When it is supplied by electricity, the wire warms up. So it's the floor heating part, and they used to have air supply on the floor. There are some ventilation vent to supply air.
Oh.
Yeah, and
under the floor.
Yeah, from one side.
Yes.
Yeah, from one side to supply, and the other side to return. And in this mode, a lot of energy is costed. Because when the air is supplied to the church, there are an extra part of air should be heated. And also the air supply temperature is lower than the indoor air temperature. So the floor heating also have an extra heating for the air supply here.
Okay.
Yeah.
Understood. Yes.
Then now they just turned off the ventilation because of a lot of energy use. There is some small fans, like very small fans on the balcony of the church. It just extracted air from the church to outside, no supply air. So there is no heat recovery, just extract
I see.
air. Yeah.
I see. So those are the two systems, and the main heating really comes from the heated floor, from underfloor.
Yeah.
Okay. I have a question here from Dietmar Holzer, and the question is, could you explain why PPD decreases when the rel H increases? Shouldn't it be vice versa?
I think it's here. The PPD, the PMV and PPD is a mathematical model to predict the thermal comfort. It can be traced from the study of the Denmark group of thermal comfort, the Professor Fonger. They conducted a series of thermal comfort study there. The basic theory, the start point of their theory is from the summer condition. So in summer, the relative humidity has more effect on the thermal comfort, because as the experience we have, when the relative humidity is very high, we will feel warmer than when the relative humidity is lower. But when it comes to the winter condition, the relative humidity has less effect on the thermal comfort. But the mathematical model for the PPD is still the same with the summer one. So there are so the PPD will decrease when the relative humidity increase.
Just during winter?
Yeah.
Yeah. Okay. Now, just one rather ingenious question. With so much heat loss from the fabric, is it not possible to insulate the fabric of the building at all?
Yeah, it's actually it's a good way to give more insulation of the wall, but the church is kind of a special building. People don't like have any change for the envelope or for the outside view of the church. They don't want to change.
I see.
Yeah, they don't.
So it's a decision taken really to not insulate the fabric, and that is in a way behind the high level of expenditure. So what you're left with is looking at how to manage the energy use, the heat use very carefully in order to maximize the efficiency.
Yeah.
That's very clear. Now I'm going to ask everybody to unmute their microphones if you'd like to ask any further questions before we wind up. I don't know if you can or if I have to do it in the, let's see. I'll see if I can unmute microphones here.
I should pass the host to you now.
Oh, yes, please.
I have passed to you.
Okay, oh. Sorry, I can now see that there were people waiting to be admitted, unfortunately, because I didn't have the host. I couldn't admit them, and I'm very sorry about that. Yeah, we were just basically saying we've come to the end of the presentation. The presentation will actually be, has been recorded, hopefully, and will be uploaded onto the project website. Now, what we we're looking for is any more questions. We haven't got any more questions written there. I also am trying to see if there's a way of unmuting the microphones, but just to see if anybody's got any final questions that they'd like to make personally. If you just give me a minute, I'll do that. Just 1 second, please. Okay. I should now have unmuted. All the microphones can be unmuted. So if you'd like to, if anybody would like to ask any further questions, you can unmute yourselves by pressing the button and ask any further questions that you might want. I think. That doesn't seem to be working very well. No one seems to have been able to unmute themselves, so it looks like if it's...
Well, maybe another
yes,
question.
I can hear somebody.
This is Dietmar Holz now.
Yes, Dietmar.
Hello.
Hello.
Have you noticed some regularity in the when you check in the differences of the calculated heating demand and the measured heating demand? I mean, are there? Because I have noticed, as I remember, that there are in the first part of the year, the calculation results are not. It was some slide before when you compared.
This one?
No, before. I think.
Here.
Here, yes. And you can see that simulation results in the first part of the year are lower than the measured ones, and the second part, simulated or some simulated results are higher. But indeed, are only two. In May, in September.
Yeah, these two.
Are there any reasons for this behavior?
Yeah. As there, you mean here?
This
and
one, yes,
here.
And in November and also in May.
Yeah. Maybe there are. It has some reason about here. When the simulation is carried out, the climate data was used. The climate data is from the database of ASHRAE, and it's not exactly the same with the real climate when the measure is carried out. So the difference may be from the climate data. And also in the church, when the temperature is controlled, it is controlled by the staff. They use the their cell phone to heat more or heat less to control the heating. So when he controls the heating, it's kind of based on what temperature he felt, not as precise as the simulation model, because in the simulation model we set a specific air temperature, and the calculation will use that temperature. But in the real case, people controlled the temperature. So
Okay.
maybe it's the reason.
I see.
Okay. Thank you.
Yeah,
Thank
thank
you.
you.
There's this problem always between the calculated models being different from the measured models in all sorts of energy efficiency measurements. We find this all the time, that the calculations that you can make are very rarely, if ever, the same as the ones that you actually get when you measure, because there's a certain unpredictability of conditions and human behavior that you can never really factor into measurements. Okay, are there any more questions? We're getting close to the time of winding up. If not, I'd like to thank Ying and her colleagues at Umea very warmly for having shared the very interesting and cutting-edge results of your research and your methodologies. And it's a fantastic contribution to the Energy Pathfinder project, much more detailed in a way than what we're doing in the other demonstrators, and no less valuable for that. So we wish you every success with your continued research in this area. For all of those of you who have attended, thank you for coming. I'm sorry about those of you who were left in the waiting room. Because of the changeover of hosts, we didn't really see you there. The recording will be put up on the Energy Pathfinder website and possibly Facebook and YouTube links as well, all things being equal. So you will have an opportunity to see it again and the various questions that were asked. Finally, I'd like to invite you all to continue following the Energy Pathfinder project. We will be hosting more webinars in future. We look forward to any views or feedback that you might want to give us, and indeed any themes that you think you might cover. The project will run for about 2 more years now, and there'll be a lot of interesting research and demonstration going on. So we hope we'll be able to come back to you with further exciting and relevant webinars for you. Okay, so I'd just like to thank you all, and thank Ying in particular, and we'll finish here. Keep safe, everybody, and we'll see you again soon.
Yeah, see you.
Bye.
Thank you. Bye.